I'm Mike Pritchard. I'm a numerical climate scientist by training. I've been on the faculty at the University of California, Irvine for a decade. I'm part of the LEAP project as a multi-institutional center. And about a year ago, I joined NVIDIA. I want to mention that conflict of interest and emphasize that I'm speaking exclusively from my NVIDIA side today. But yeah, really excited to share with you some of the ways NVIDIA is integrating into the climate community, and already has been. So I want to start with this slide. I'm a climate nerd. I obsess about this problem. I wish we had high-resolution predictions of 2100. It's just a computational problem. Climate scientists bring supercomputers to their knees. Right now, we're about here, 2020, or 2023. We have to cope with 25-kilometer climate simulations. I'm sorry about that. We need to be here. We need to be providing sub-kilometer risk. We need to be resolving storm dynamics. And it's just a computer problem. We know how to write down the equations to get a lot of these dynamics. So anyway, this is one way that NVIDIA is integrated into the climate community already, is because they build supercomputers. This is the next greatest supercomputer coming out of NVIDIA that will be bought by some at the Swiss Supercomputing Center. It uses the Grace Hopper chip. And I know that some European climate scientists are very excited about its potential to run global cloud resolving models, next generation climate models. So NVIDIA's got a lot of giant supercomputers that Earth system scientists use around the world. These are a few of the ones that have exascale capabilities. This is how I discovered NVIDIA, because I work with the DOE on my academic side and experienced the GPU supercomputing revolution. It kind of changed my life. My climate code ran 100 times faster. We could do more ambitious calculations. So there's very interesting changes in supercomputing going on in the age of GPUs. NVIDIA, as a result of these interactions, this slide is meant to be overwhelming, works directly with people who develop atmospheric simulation codes to show them how to refactor them to take advantage of new architectures and achieve the kind of speed ups that we really need to get to high resolution impacts predictions. Okay, but today I mostly want to talk about artificial intelligence, because NVIDIA is much more than a hardware company. It's a full stack AI company. Its deep learning engineering expertise and its hardware have fueled the iPhone moment with AI that's going on, and ChatGPT, et cetera. And this has been my main interest. So, you know, LEAP wonders whether we can bypass Moore's law in many ways by using artificial intelligence to get high-resolution physics into climate models. And you know, I think that's a very exciting direction to be thinking right now. So now I want to mostly tell you a story about how this is already happening in weather prediction, how AI-based weather prediction is completely disrupting the business of predicting the medium-range weather. So let's talk about weather prediction. Weather prediction is normally done by central government agencies as a public service and then consumed by an ecosystem of downstream users. Those public agencies also require a lot of computing. This is the best weather modeling center in the world, the European Center. That's their supercomputer. They need a lot of computing because they have to predict the next 10 days dozens of times to give us a probability distribution of the possible outcomes to plan. And we are, of course, especially concerned with tail risks. You want to hope for the best and plan for the worst. So for the entire history of weather prediction, there's been this tension between how you spend that compute on resolution. You'd like more of it to resolve damaging storms, or ensemble members. You'd also like more of those to understand the worst storm. So this is AI weather prediction. It's completely different. It's not solving physics equations on big computers. It's more like training a big transformer model, much like ChatGPT learns to predict the next word from the entire internet, but to learn instead how to predict the next 6 hours temperature map from the current one. So it's like video prediction, fully AI video prediction, but instead of pixels with red, green, and blue, we have temperatures, winds, and pressures, et cetera. And we don't have the entire internet of human words to work off of, but we do have like 15,000 days of reliable satellite observations and best estimates of the observed atmospheric state. And so that's not humans writing things, that's physics, observations of the real physical atmosphere. And this is being explored by several companies. And it's remarkable that small teams of deep learning engineers inside these tech companies are producing rapid skill gains. That includes NVIDIA. This is our forecast model. We were proud that it was one of the first ones to try to achieve this ambitious 25-kilometer resolution a year ago. Lots of people are there now. These are some statistics about it. It's fully AI, but this green thing is the main point. Once trained, this model can predict 2 weeks of weather in 1/4 of a second on a GPU. And that's a 10,000 times speed up compared to classical weather prediction. And that has profound implications. Only if it's skillful, of course. This is the skill. So sorry to show you a graph, but this is days into a forecast, and this is an accuracy metric, and yellow is the gold standard baseline from the European Center. So of course, accuracy decreases as you go further into an unpredictable weather forecast. The whole game of weather prediction is to push this curve to the right as far as you can. This is where NVIDIA was about a year ago with our fully AI model. And the main thing is the difference between that purple line and the blue line. That's just a few months of some deep learning engineers tinkering with stuff. And so the skill gains, the rate of skill increase is really impressive. And I can say we're really close to the benchmark now. And some other tech companies published some wonderful papers this year that have actually claimed that they have better skill than the world's best weather model. DeepMind has claimed this, and Huawei has claimed that. So this is happening all around us. This is the year. And compare that to the quiet revolution of weather forecasting that Pierre mentioned. Indeed, forecasts have gotten much better since the 1980s. They're more reliable, but it's a slow process. And what's going on with AI is really fast in comparison. What are the implications of this for solutions and for those of us thinking about climate prediction? Well, I mentioned this tension between the resolution, which you would like more of, and the number of ensemble members that you would like more of, the resolution of the probability distribution. This tension is gone. The once trained an AI model is trivial to inference, and so we can produce massive ensembles of weather forecasts. 10,000 member ensembles we're running these days. And so if you want to, and these ensembles are geographically explicit, they look like real weather predictions. I mean, the statistical skill is unambiguous. But now we can finally resolve that tail risk in 10,000 member ensembles, including its geographic detail. And so I think that's an important capability. It's entangled with a bunch of gnarly technical issues about how you process all the data. And there's an interesting tension between storage and analyzing it the usual way on disk versus doing the diagnostics internally on the GPU. I think there'll be more of that just due to the breadth of these ensembles. We care about low likelihood, high impact extremes in climate. They're going to get worse. We had one this year in California. Random confluence of Rossby waves that happen to deliver a unusual wet season. Maybe there's some climate forcing in there too. But that's an example of an impactful tail event that requires a rich PDF to try to anticipate. Here's another one, the Pacific Northwest 21 heat anomaly, 6 sigma event, town ignited in Alberta. The science of studying these low likelihood extremes stands to benefit from these AI methods of producing weather. So this is Bill Collins. He's a famous climate scientist at UC Berkeley. He's been studying impactful extremes for a decade, and he's recognized that this order of magnitude increase in our ability to emulate accurately the historical weather opens up the possibility to finally get good sampling of low likelihood, high impact extremes to start to understand the climate drivers there so that our knowledge base increases about how the climate drivers of impactful extremes will change in the future. So that's one collaboration we're pursuing. Of course, for the physicists in the room, ensembles only have value if they're well calibrated. You need to worry about this with AI models. The spread of an ensemble should grow at the same rate as its skill. And just to mention that we're beginning to achieve results that pass these kinds of tests as well. But yeah, it's a very, very exciting time in AI weather prediction. I want to also mention the link, though, between this weather prediction advance and climate interactivity and how we interact with climate prediction data. Because I think the same technology has a lot of benefit there. So here I want to talk about paradigm shifting moments in our appreciation of our planet when people first went up in hot air balloons and saw the sky and went inside of a cloud, when people first flew in airplanes and could witness the organization of clouds, when we could go out to space and actually see the physics of the remote clouds over the ocean and the many scales that they organize on. Think about the satellite era and how it just changed so many people, and so much science and technology emerged from people finally being able to draw connections and flip through images they'd never seen before. I think we need such a paradigm shifting moment in climate. I feel that this room tends to agree with that. But there's this problem of how do you interact with these petabytes of obscure data that are hiding on disks? And it takes expertise to get at them. We saw a wonderful solution that LEAP is innovating, but there's latency problems here to get at the real richness of these data, their spatial temporal details. And I think these same sorts of AI weather models that run blazing fast that simply interpolate the historical record can easily be retrained on future climate predictions, on our library of climate predictions, make it much easier to interact with the predictions just by inferencing them locally on a GPU to get at the latency issues. And so you could imagine building digital twins of existing libraries of climate predictions and then using them as a back end for the sorts of visualization systems that Leap and others are developing to make it easier for stakeholders to interact with existing predictions. So that's something we're interested in at NVIDIA. You can imagine grander visions as well of digital twins at many scales interacting and linked together. NVIDIA's got experience building digital twins of viruses for drug discovery with AI and of infrastructure for people who build factories, which they're often doing in virtual environments now and optimizing them there before breaking ground. And then I mentioned our planetary digital twin of the weather. But there's a vision out there for the world to try to self-assemble networks of digital twins that can allow us this paradigm shift to see our agency, for businesses to understand their agency, their feedback, how decarbonization in North America actually interacts with the spatially explicit hazards of the future. So Earth-2 is an initiative at NVIDIA that seeks to dream about this vision, to imagine how the tools that we're developing in our tech company could help the world enable it. The world is, of course, already working hard on these problems. I'm impressed by the transition from academic to operational climate prediction that's happening in Europe as part of the Destination Earth project that is thinking about these linkages. And NVIDIA has tools that I think would be helpful here. There's Omniverse, I'll talk about that, Nucleus. Modulus, I want to mention, is our platform for physics-informed AI. Industry uses it. It's now open source, and it contains these digital AI weather models that I mentioned. And so if you want to use them, they're available to the community. And I mentioned our supercomputing. But Omniverse is a place to congregate, to connect things. It has a component called Nucleus that is a shared place where models, data, tools, services, and applications synchronize. It's used by the clients that use NVIDIA's physical infrastructure digital twinning to allow tight links and feedbacks between the sorts of components we need to link together, from infrastructure to climate predictions across scales. So, and lastly, I'll say this is not an internal initiative within NVIDIA. It's meant to be collaborative and complementary. And we think that at NVIDIA, there's expertise in visualization and hardware and engineering, and especially full stack AI expertise that's going to be important for the world to help build these more interactive, paradigm shifting understandings of our place in the planet. So thanks for your time.